Hi there. Those are here. Sorry, a few minutes late started, but yeah, so I'll wait a minute or two. See if anyone else is joining. I don't know if people found it confusing as to like where to go to do the review, or maybe people are just figuring they'll watch the video or whatever. Well, wait an extra minute here until I get going. All right. Yeah, so we'll see kind of how this goes here. So I don't have prepared a large number of example problems or questions or things like that, right? Again, because the idea of this review is to answer questions from students and things like that, go over whatever things people have questions about. I will start off real quick. So, you know, feel free to start thinking of questions and such, typing them in chat, or you can verbally ask them in just a minute when I'm kind of done with my spiel here. But I'll just kind of first start off, talk a little bit about kind of general information for the exam for those here, those who are watching it via Zoom or this video online, as it will be posted to the YouTube channel as well as Canvas. So a couple of things in terms of what equations are given, we have the ones listed here, and that's sort of it, right? The first two equations, the change in freezing point temperature and boiling point temperature, those are related with like colligative properties, right? I is your Van Hoff factor. It's an integer, 1, 2, 3, 4, 5, so on and so forth. Kf, Kb, or freezing and boiling point constants. They depend on the solvent, and they would be given, right? You don't have to memorize what those are. M is your molality of your solid, right? Of your solution. Okay. The next three equations are related to integrated rate laws. The logarithm of concentration of A equaling minus KT plus ln concentration A, and concentration of A equaling concentration of A naught, E to the minus KT. Those two equations are both for their first order integrated rate law. Okay. And then the second equation there, 1 over A equaling 1 over A naught plus KT, is for your second order integrated rate law. Okay. Those are the equations that are given for this exam. Okay. Any other potential kinds of equations or formulas or other things like that that you feel like you need to know to answer a question, or you need to know those formulas yourself, right? You have to have those kind of memorized and remember when to use them, when to apply them. Okay? So in terms of kind of things to know, so I kind of highlighted the main points of the chapters, which are, most of the chapters, but still just kind of trying to highlight some of the points of 3 chapters we have covered and are going to finish covering on Monday with chapter 14. Okay, so for chapter 12, right, the main thing is knowing your types of intermolecular forces and identifying what are the dominant intermolecular forces for a given molecule. Okay. Right, and then understanding the relationship between those intermolecular forces and properties of your molecules, right, when they're in the solid phase, liquid phase, and things like that, right, boiling points, melting points, vapor pressures, and such. Okay, and then knowing your like phase diagrams and the heating curves, right, understanding kind of what those are, being able to label them and such. Okay, so those are kind of the main things, concepts, ideas from chapter 12. Chapter 13, right? First thing, like dissolves like, right? Is meaning, right? You need to, right? Understand what things dissolve in what things, right? There's basically, right, similar intermolecular forces between your solute and solvent mixed together and dissolve. Okay, right? Your solution vocabulary, saturated, unsaturated, right, supersaturated solutions, miscible, immiscible liquids, those type of things. Henry's law, right? A big one in chapter 13 is your concentration units, knowing what is the definition of molarity, molality, parts per million, mole fraction, mass percent, all those different concentration units. We need to know what the definitions of those things are, okay? Because you need to know that in order to be able to apply it to given problems that rely on those concentration units, whether it be, right, your colligative properties, right, in this chapter that use molality, okay, whether it be other things like chapter 14 and such, you use molarity, right, or just questions within this chapter converting between these units, right. In order to do these things, you need to know what those units are. Okay. And then obviously convert between them, and then know your colligative properties, right? Your freezing point, depression, boiling point, elevation, and vapor pressure decrease, right? Lowering of your vapor pressure. Okay. And finally, for things to know for chapter 14, right? We have the definition of the average rate of the reaction, right? How does that relate to the rate of changes of your reactions and products, right? Those kind of formulas between the average rate and 1 over the stoichiometric coefficients for your reactions and products, right? What is the rate law, right? What is it telling us? What are the things in it, right? The rate constant and such. Being able to solve for those rate laws using something like the method of initial rates, which is what we spent a lot of time on Wednesday this week doing. Okay. Your integrated rate equations, then things we're talking about on Monday is what are reaction mechanisms, understanding those, what's an intermediate and such, collision theory, we'll talk a little bit on Monday, and catalysts, okay? There aren't a lot of example problems really with collision theory and catalysts. Those are more conceptual, so we'll talk about them briefly on Monday, but I very much recommend you check out the lecture videos online to get more detailed kind of discussion about those concepts and topics. Okay. All right. And then about the exam, right? So it's going to be 60 minutes, and the idea of doing this is because, again, for our final exam, because this class is split into 2 groups, the final exam, one group will take, right, the exam for kind of the first hour. Then there will be a little bit of break as people shuffle in and out, right? And then another group of people will take an exam for another hour, right? We have the class for, I think, 3 hours or 2.5 hours, something like that, right? And so we have to get everyone to take the exam during the regular exam period. And so because that final exam is going to be an hour, so I'm just making all of the exams kind of an hour to be consistent with that. There will be a mixture of multiple choice and long answer questions. Okay, you will be given a periodic table and those equations I mentioned earlier on your hard copy of your exam or on Canvas. It will be the very first question in the exam will be labeled as a periodic table and in the equations. Okay, something to write with and scratch paper. But if you use scratch paper, I need to see it before you start using it, right before the exam starts. Right, make sure you don't have notes on there. Okay, and finally, don't discuss the exam with classmates, right? Because things are broken up. Half class is taking the exam one day, the other half is taking the exam the other day. Okay, you're only hurting yourself by giving the other students an advantage because typically the exams in this course end up being heard, and so I very much recommend you don't do that. Okay? I mean, there's not too much to discuss because the exam will cover the 3 chapters I mentioned and have plenty of example problems from each, so there's not really too much advantage you can get. Yeah, question? Yeah, so at the beginning here, so these are the equations that are given. And I'll post these review slides online as well. But basically, whatever so there's the, what's it called? Final exam sheet, I think is what it's called on Canvas. It ends up, it's kind of like an orange colored document, like when you open up the file, so I just scanned what's given on the ACS final exam. And so all the equations on that document are the only equations that are ever given in class. Now there are more equations than these, but all the other equations are not relevant to what's on this exam. And so I just don't bother putting them just to not clutter things up with a bunch of equations that are completely irrelevant to what we're talking about. So yeah, but yeah, so these are the equations. There aren't too many I mean, again, the equations I can think of is like Henry's law and your definitions of concentration units, if you consider those kind of equations, right? Molarities, moles per liter, like that type of stuff. And then otherwise, your rate law, I guess, is sort of like an equation. But like integrated rate laws, colligative properties, those are given, right? Yeah, so there really aren't very many equations per se you actually have to memorize for this exam. But any questions so far from people on Zoom right now? So you can either type them or feel free to speak and ask them verbally if you prefer. Yeah, myself as well, but that's fine. So yeah, for those on Zoom, which actually is not very many people on Zoom as well, we have one lovely student joining us here in class right now. But yeah, that's fine. You know, it is sort of a late minute announcement, and that's, you know, people have things that they got to do, or you know, it's not a required thing whatsoever. It's kind of doing it is helpful if you need it. Yeah, so I will definitely, Valerie, I'll definitely do an example of conversions between concentrations. I'll just make a brief note here. Last thing I want to just talk about is for those who are taking the exam online, right? I sent an announcement on Canvas to those people already, but in case you didn't read it, didn't look at it, just kind of highlight some of the points here, and I'll probably highlight them again on Monday, okay? Right, the exam will be on Canvas, okay? It will only be available during the regular class time of like 2 to 3:20 p.m., okay? You're broken into groups, so on Canvas is a list of you know, students who are taking the exam on Monday and those who are taking it on Wednesday, and that will be consistent for the entire semester. So if you have, right, the next exam, the first day of taking it is on a Monday, and the second day of taking it is on a Wednesday. So, right, so again, I tried to, like, alternate that so it's not that every time the Wednesday people have to take it before the Monday people, right? It's alternated, but so the group you're in for this exam will be the same group you'll be in for the next set of exams as well. You should try to log into Zoom at least something like 15 minutes before. Make sure your camera's set up, everything's set up. I will be here 15 minutes before class to answer questions, check out people's setup, and make any comments about, hey, you need to close this or that, or need to put away this thing or that thing, right? Just to make sure everything's ready to go for when the exam starts. Okay. For those who are taking it online, right, the long answer questions, numerical answers, questions on Canvas, and you can't show me your work through that, right? And so what I'm going to have is this. So this has changed since the announcement. I decided to do it this way, so that people aren't pulling out their phones while taking the exam and things like that. After you've finished and submitted your exam, okay, then what you can do is you can then, there will be a separate kind of quiz on Canvas that will be labeled exam 1 upload. And on that quiz, there will just be one question, and it'll be just a question where you can upload your work for the long answer questions for credit on those questions. Okay. So if you want to earn partial credit on the long answer questions, make sure you're writing out what you're doing on your scratch paper, and then I prefer using the Adobe Scan app, but if you don't know how to use it, don't want to use it, take a picture or whatever you want to do, right, to upload that work onto Canvas. Do so then, right, and you'll do it to this kind of exam 1 upload quiz thing. Okay. All right. And so that's it for kind of the notes about kind of the exam and how it's going to be done and things of that nature. Hopefully kind of clear. So before we get into some, so before we get into the example problems, I'll make sure there are any other questions about just kind of the format things. So yeah, so one question here from Zoom. So we have the question, would we upload it at the end of the exam, right? Would you upload the exam or your work at the end? Yeah, so how it will work is you won't, the actual exam, when you open the quiz, I will say like exam 1 or something like that, right? That exam, that quiz that you're taking on Canvas won't have anything there to upload stuff. What you'll do is you'll just answer the questions. For the long answers, you'll fill in your numerical answers, type in your number 12.5 or whatever, right? And that will be it. Okay? And then when you submit and you finish taking that, then you can go ahead and open up another quiz, right? That will be there for file uploads, and that quiz you then will upload your files to. Again, the name of that quiz will be something like exam 1 upload. So you'll do that once you're completely done with your exam, because again, while you're taking the exam on Zoom, a lot of people will be using their phone to log into Zoom and have the camera point at their computer as they're taking the exam, right? So I don't want you grabbing your phone, trying to then scan your work and things like that, or potentially going to a different website to upload it or whatever the case may be. So I want so your exam will be completely finished and submitted before you try to upload anything. Okay, because once you start the exam, you should not leave the exam page on Canvas, and that's why, I mean, one, you should be having a camera showing your computer so that I can see if you do leave your exam page. And 2, Canvas lets me know if people leave the exam. So for example, when people are taking the quiz, I can tell when you switch away from looking at that tab on your browser, okay, and start looking at something else, right? Now I can't tell what you're doing, right, when you're doing it, but I can tell that you've left, right? And for the exams, you should not leave that tab, right? You shouldn't have any other tabs open or anything else like that, right? And so I want to keep it that way. So you submit your exam, and then you can just go to the other quiz to upload your work. And you'll have some extra time to upload that after you've submitted the exam and such. Okay? That kind of clear it up, hopefully. Hopefully so. And for those who are here on Zoom, if you want to, after we're done with this, figure out and check, you know, hey, would this setup work or something like that in preparation for Wednesday or Monday, I'm happy to stick around and look over how you would have your camera set up and work area and things like that. Okay. But yeah. All right. So let's pull out some paper here and a pen, and we'll get started on doing some. First example we will do here are conversions between units. Okay. So concentration units. So we'll do some concentration conversion problems first, and then kind of see from there. Let me find blank pieces of paper that I'm sure I have. All right. All right, so now I'll turn my lovely face down here so we can look at kind of the documents. That around, you share. All right, here. Okay, so first thing is converting between concentration units. So, right, let's say what we have is we have a solution that is 0.025 molar with actually I should say what, like of, let's just say salt, sodium chloride with a density of 0.98 grams per milliliter. What is the say the mole fraction of NaCl? Okay. So again, so I have like a sodium chloride solution, right? So the solute is sodium chloride, the solvent is water, right? The concentration and molarity of that solution is 0.025 molar. I'm given the density is 0.98 grams per milliliter, and I'm asked what is the mole fraction for this system. All right, I think it's a little bit clearer there, right? All right. So when we start these problems, right, these conversion problems, especially the first thing I like to try to do, right, is I think, okay, what are these concentration units? What the heck do they mean, right? So molarity is defined as moles per liter, right? Moles solute per liter solution. Okay. Right? While the mole fraction right of NaCl is the moles NaCl divided by the moles total. Okay? Right? So these are my different concentration units that I need to know, right? And so this is why it's useful to know what those concentration units are, right? If I don't know what they are, I don't know how to potentially convert between them, okay? So the nice thing, right, is I already know the moles, say, of my solute, okay? Right? Moles of my solute. Like if I know the total volume of my solution, right, I know the moles of my solute, and that just goes here, right? Sodium chloride's the solute, right? If I need to know what the total moles are and things of that nature, right? And so I need to somehow find the total moles, which is the moles of sodium chloride plus the moles of water, which is our solvent. Okay? Now, right, in these problems where I don't know what the total amount of solution I have, right, often we're told, you know, in these problems, we're just told concentrations, we're not told the total amount. And that's just because it doesn't matter what the total amount is, right? But we should assume some total amount. So here I'm going to assume 1 liter, okay? And I assume 1 liter because I'm given a molarity, and in molarity, my denominator is liter, right? So I'm going to assume 1 liter of solution, right? And so my molarity tells me in that 1 liter solution, I have 0.025 moles of NaCl, right? So if I assume 1 liter solution, that means I have 0.025 moles of sodium chloride, right? And so I have the moles of sodium chloride, so that's great. I already got the numerator here in my mole fraction. I just got to figure out what the denominator is, right? And to get that, I need to know the amount of moles of my water. So I got to figure out somehow I can get the moles of my water from the volume of the solution. Okay? And so we do that using the density. Okay, so the density, right, allows us to convert between mass and volume. Okay, so the density here, I have 1 liter of solution, right?
Can you always assume 1 liter or like per se like 100 of something?
I like to assume nice numbers like 1 or 100 or 10 or something like that, just because it makes the problem easier. But you could assume any amount you wanted. I could have assumed 5 moles of sodium chloride and used that to figure out everything else. I could have assumed, you know, 0.125 liters or something like that, right? Like the amount you assume doesn't change your final answer, but it does make it a little bit easier if you, like, again, why I picked 1 liter solution is because I have molarity, which my molarity has liter of solution on the denominator. So I assumed 1 liter of solution, so I could take 1 liter times my molarity to get 0.025 moles of sodium chloride, right? So it just made that math a little bit easier, and it makes some of the math easier later on, right? But if I assumed a different volume of solution, I would get the same answer, just the math, you know, may or may not be more difficult, right? So by more difficult, I mean you might just have to plug in more numbers when you multiply stuff and things. It's not really, you don't, there aren't going to be more steps. It's just, right, I can do in my head 1 times 0.025, right? But if I picked a total volume of 136 liters, right, then 136 times 0.025, I can't do in my head. So I'd have to, you know, use a calculator for it. But, and so if we want, again, we want to get the, we're trying to get the moles of water, right? That's what we need to get the total moles, right? So I take my volume of the solution and I use 0.98 grams, 1 liter. Oh, shoot, I did that completely wrong. Sorry, shouldn't divide by it. Let me start again. Okay, that's a mistake. I shouldn't be dividing by it, right? As you saw, the units didn't cancel, so that doesn't make sense, right? I have 1 liter of solution, right? And I know I get 0.98 grams for every 1 milliliter, okay? Well, I have milliliter, that's liter, right? So I gotta do 1,000 milliliters is equal to 1 liter. Okay. Right. So now my liters cancel, milliliters cancel, right? And I'm just left with grams, right? And so this is going to be 980 grams of solution. Okay. Right. And what's in my solution, right? In my solution is my solute and my solvent, right? So this is 980 grams of solution is the mass of NaCl plus the mass of H2O, okay? And this is what we're looking for, right? We want to try to find the mass of water because that can give us the moles of water, okay? And so, right, but in order to get that, I need to find out what is my mass of sodium chloride, right? And so we get that from the moles of sodium chloride, right? If I take my moles of sodium chloride, multiply it by my molar mass of sodium chloride, which, again, you'd be given a periodic table to be able to do this. 35. So the molar mass of sodium chloride is roughly 58.45 grams per mole. So that times 0.025 gives us 1.46 grams of sodium chloride, right? And so now, going back down here, now I have the mass of sodium chloride, I have the total mass of my solution, so now I can get the mass of water, right? So I have 980 grams equals 1.46 grams plus the mass of water. And so I just take 980 and subtract off 1.46, right, to get 978.5, just kind of rounding up here, grams, right, equal to the mass of H2O. Okay. So now I have the mass of water, right? So finally, I can use its molar mass, right, which is 18 grams per mole to get the moles of water, right? So the moles, right, so if I take 978.5 grams of H2O, and I divide that by its molar mass of 18 grams per 1 mole, that will give me 54.4 moles of water. Okay. So that's how many moles of water are in my 1 liter solution, right? So I took my 1 liter solution, I converted that volume to a total mass using the density. I then use the fact that the total mass is the mass of sodium chloride and the mass of water, and subtracted off the mass of sodium chloride to get the mass of my water, and then I use the molar mass of water to get the moles. So finally, I can get the total moles and the moles of sodium chloride, right? So my mole fraction here of NaCl, right, is, what did I say? Oh, shoot, sorry. I'm going to bump that. Right, is 0.025 moles over 54.425 moles. Okay, so the total moles, right? I just literally took 54.4 plus 0.025 to get the total. Okay, so 0.025 divided by 54.425. That gives me a final mole fraction. I'm just going to write it over here. I didn't give myself a lot of them. I apologize about that. But the final mole fraction, final answer is 0.0. I'm going to write this. Mole fraction is 4.6 times 10 to the minus 4. Okay. That is my final mole fraction. Okay. All right. So again, let's just briefly go over what we did, right? In the problem, we needed to convert from moles per liter to moles per mole, basically, right? To do that, I assume a total amount just to make everything a lot simpler. Even though it may not look simple, I promise you it is a lot more challenging if you don't assume a total volume or a total mass or something, okay? So we assumed a total volume of 1 liter just because the molarity that we're given is in per liter, okay? That told us I have 0.025 moles of sodium chloride. I eventually needed to convert that to grams, so I used the molar mass to convert that to grams of sodium chloride, okay? I then used the density to convert the volume of my solution to a total mass of solution. I then subtracted that total mass by the mass of sodium chloride to finally get the mass of water. And then using the mass of water, I can use its molar mass to get its moles. And then now I finally have the moles of water. I can add that to the moles of sodium chloride, get the total moles, put in the denominator of my mole fraction, which was 0.025 moles over 54.425 moles, which gave us this mole fraction of 4.6 times 10 to the minus 4. Oh, so that is, so the 58.45, this is the molar mass of NaCl. Sorry, I wasn't very clear on that, right? So if you calculate the molar mass of sodium chloride, right? If I ever want to convert between moles and grams of something, right, use the molar mass. And so yeah, that's the molar mass of sodium chloride, right? So again, sometimes that might be given in a problem. Other times it won't. And when it's not, you need to use your periodic table to figure out what that is. So. So sorry, what I did is I took 0.25 and I multiplied it by 58.45. Yeah, no, yeah, that's yeah, that's true. That's not very obvious that I decided to take this number and multiply it by that. Yeah, yeah, 58.45 equals 1.46. Doesn't make any sense, right? Yeah, thank you. Yeah, no, that's I took my moles of sodium chloride and I multiplied it by the molar mass to get the grams. Yeah, so yeah, so that's where I did that and why I did that. So I apologize. I wasn't very clear. But yeah, I multiplied the moles of sodium chloride, which is 0.025, by that molar mass of 58.45 to get the 1.46 grams. Other questions about this question? All right. Conversions using molarity are one of the more difficult ones to do because molarity is the only one that uses volume. And so you need to use density to convert between that volume and masses and things like that. And so the most steps are typically involved with molarity conversion. Okay. So so yeah, that's definitely the more complicated of the type of conversions, is converting from molarity to something else, which is why I picked it for us to work on that together. Okay. Yeah, most of the other types of conversions just involve using your molar masses to convert between grams and moles, right? Because everything else uses grams and moles, and that's it, right? Molality uses moles and kilograms of solute or solvent, right? Mass percent just uses masses. Mole fraction just uses moles, right? Parts per million, parts per billion, those just use masses, right? So it's molarity is one of the only ones that uses volume, and it uses volume of solution instead of like volume of solvent or things like that. So again, it's a little bit trickier with molarity. Other types of things people want to go over. If someone wants to see another conversion problem, we can do another conversion problem. But I'm happy to go over other types of questions, whether it be example problems or if people have conceptual questions as well. I'm happy to answer those. Huh? Yeah, yeah, I'm happy to do another conversion one. Right.
And also, do you have any like tips on like what the best way is to like study for this or like understand like problems? Because like my biggest thing is like for chemistry is like I look at a problem and I either overcomplicate it or undercomplicate it.
Mhm.
Like if that makes sense. And like I don't know, I just like see it and like I know what to do. Like once I have the numbers, but just like figuring out like where to get started is literally the hardest part. And like
Yeah.
I don't know how to get over that.
Yeah, I mean, and that's one of the more difficult parts. I mean, so I also teach upper level physical chemistry class here, and that literally is the entirety of like the course is just trying to interpret like a problem into like how do you start, what equation do you use or whatever to like do what you need to do, right? What path do you follow? That's definitely the most difficult part, and it also is one of the more difficult parts in this class as well. For a lot of these types of problems, is just identifying what is the problem and what you need to do. And so, yeah, in terms of those things, I like to try in my head, like to break things up into like, okay, this is a conversion problem, or this is that, like certain different types of problems, right? Because like a colligative property, a conversion, um, a method of initial rates, rate laws or things like that, right? Those type of more kind of long numerical answer type problems. Um, I kind of categorize them into different things, and then in terms of approaching them, for a lot of them, it's what do I use or things like that, or where do I start? I like to try to write down what information I know about the problem. So just as kind of review again, in this problem, the very first thing I started with is writing down what is molarity and what is mole fraction, and then thinking about, and I can kind of talk about the thought process in a little bit more detail, right? But thinking about how can I get from one to the other now that I know kind of what these definitions are. So we'll do that in a little bit more detail in this next example, right? So like if I have a colligative property example, I would, be like, okay, well, what's the relationship for that colligative property, right? Like delta TF equals I KF, M. Okay, then what are the values in that equation, right? That and things like that. So, but yeah, so and in terms of practice and things, it's really just doing plenty of example problems. Taking the practice exams that are posted, reviewing the quizzes that are on Canvas, reviewing homework questions. There's extra questions on sapling. The back of your textbook has example problems, and I even have solutions to, I forget if it's the odd or the even number of questions for the textbook. Why am I saying the back of the textbook? It's an online textbook, right? So in the online textbook, each chapter has examples, and I have solutions to either the even or odd posted on Canvas, and they're detailed solutions too. So right, like the solutions to the quizzes and things like that are just like a number, right? This is the answer, right? If you don't know how to get there, it's not as helpful, right? But the textbook, the solutions that are posted on Canvas are detailed, worked out solutions for every problem that are there. So that's another good resource to use if you want to see the answer worked out in detail, so you can kind of try to follow along and try to see, okay, why did they do this or why they did that.
When you said that if, like, say I do go and do the practice problems with those, like, if I am, like, get pretty confident with, like, those examples, say that more than likely I do it for me?
Yeah, I mean, and also if you feel confident about so the practice exam, for example, is an exam I wrote in previous years. So definitely, if you feel confident about the practice exam, then that's good. What I can do is I'll try to sometime today. Maybe I'll make send an announcement about it this evening or something like that. But I'll try to go through and kind of have a list of problems on the online textbook that are kind of relevant to the exam, because the thing is there are certain things that are probably in the online textbook in each chapter that we don't cover very much or very well. And so, yeah. Yeah. So yeah, so I'll come up with a list of problems from the textbook to look over and to use. So, all right. All right, so let's do another conversion, okay? So let's say here, so instead, let's say have a 128 parts per million solution of magnesium ions, Mg plus, right? What is the molality of this solution? Okay, right? So this could be another sample problem here. Okay. Often, I mean, I'll try like on exams and other things to mention it, right? But often, right, if you're talking about like a solution of something, often it's assumed, right, the solvent is water, right? Typically, the solvent is not water. It's mentioned what the solvent is. But if the solvent is water, a lot of times it's just kind of assumed that, you know, that's what the solvent is. So I'll just kind of make a note of that. I think I typically try to say what the solvent is in a problem, like on an exam and stuff, but can't guarantee it off the top of my head. But yeah, if the solvent is not given, you can assume it's water. It's not just fair. It is going to be water. If yeah. So often what's done is instead it'll say like an aqueous solution, and aqueous means the solvent is water. So that's another way that instead of saying, parts per million solution of magnesium ions in water, they would say like an aqueous solution of magnesium ions, right? So that word aqueous is telling you the solvent is water. Okay. So yeah, so again, I start off and I say, okay, what I know is I know my parts per million, right? That I have 128 parts per million, which this is related with the mass of Mg2 plus over the total mass times a million, 10 to the 6. Okay? And what I want, right? So I know this, right? What I want is I want the molality, which is the moles of Mg2 plus over the kilograms of water, right? The salt. Okay. Right. This is what I want. Okay. So so again, that's kind of what I know, what I want. And so then the question is, right, how do I get from what I know to what I want, right? And so then I start looking at what are the numerators and the denominators in these things, right? So again, my head, the first thing I look at is, okay, I have the mass of magnesium. I want the moles of magnesium, okay? So I know one of the things I'll need to do, right, like one step, doesn't, like not necessarily in order, like just like one step will be use molar mass of Mg2 plus to convert grams to moles, right? Since I know I need moles of Mg2 plus, and I'm given the mass, I know I need to use the molar mass to convert between those two things, right? Again, the order in which you do things can vary and blah, 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 but like, I just think about how do I need to get from where I want to, from where I am to where I need to go, and I know I need to get that, right? And the total mass to kilograms of water, right? Well, I know the total mass, right, is going to just equal the mass of Mg2 plus the mass of water, right? So I know I can use this relationship to figure out, right, what the mass of water is potentially, okay? And so the last step here, right, is, yeah, so if you want, we can assume 1 mole of Mg2 plus, okay? Right, and so you can assume 1 mole of Mg2 plus and do all of the problem to get eventually what you want. And let's see here. So what I'm going to do is I'm going to first do it a different way, and we'll do it both ways so you can kind of see that we'll get the same answer no matter what. But, you know, one way might be a little bit clearer than the other, depending on things, right? So what I'm going to assume, right, I see my total mass here, right? The thing I know has total mass in the denominator. So I'm going to assume, in this case, I'm going to assume 1,000 grams of solution, right? My total mass, I'm going to assume is 1,000 grams, okay? And again, I'm doing that because then in this expression for parts per million, I know 128 ppm equals the mass of Mg2 plus divided by 1,000 times 1 million, right? Which is, right, that guy, okay? So to simplify this, right, you'd like multiply by 1,000, divide by 1,000,000, and what you'll get is that you'll get the mass of Mg2 plus is equal to 0.128 grams in 1,000 grams of solution. Oh, sorry, me. All right, so in 1,000 grams of solution, I have 0.128 grams of magnesium ions, okay? And so then, right, and so here, like, what step I do next can depend on whatever I feel like doing. I can first get the moles of magnesium if I want, or I could get the total, the mass of water. Either one, right? Doesn't really matter, okay? To get the moles of magnesium, right, I would take 0.128 grams Mg2 plus, and then divide by the molar mass, which is 24.3 grams per 1 mole. Okay, get the moles of Mg2 plus equal to 128. 0.0053 moles, okay? And then to get the mass of water, right, my total mass, right, I just use this equation up here, right? So my total mass is 1,000 grams. My mass of Mg2 plus is just 0.128. And that is added to the mass of water, okay? So, right, 1,000 minus 0.128, right? I mean, right, you can, I mean, if you rounded it, you'd probably just round it to 1,000, right? But you could get, right, the mass then of water, when you solve for it, would be 999.9, you know, grams, kind of rounding it there, okay? Right, really, I mean, it's basically 1,000, right? I mean, it won't really change your answer if you just end up using 1,000, but to do it exactly right, that's our mass of water. So finally, right, I have my moles of solute and my mass of solvent, okay? Now, the mass here is given in grams, so we'll have to convert that to kilograms, okay? But we can then plug that in to get the molality, sorry, right? So the molality, right, is the moles of Mg2 plus, which is 0.0053 moles, divided by the kilograms of my solvent, right? So going back up to the top of this page, right? Molality, moles, Mg2 plus, divided by kilograms of solvent. So if I divide now my mass of solvent in grams is 999.9, right? In kilograms, it's 0.999, I guess 9, right? Again, this is basically 1 kilogram, right? And so this, when rounded, is just going to be 0.0053 moles. Okay. So when you do that division and round it to like 2 decimal points, it's going to be 0.005. Again, I'm not worried about significant figures on answers and things like that. So don't really worry too much about significant figures. But yeah, okay. And so that is how I got my molality. Okay. Now, if I assumed, real quick, let's assume instead 1 mole Mg2 plus, okay, right? If we make that assumption, what we can first do is we can find the mass of magnesium, right? Because if I assume 1 mole of Mg2 plus, well, I already know the moles of Mg2 plus. I got to find the mass of water, right? Because the mass of water, I need to find the total mass, right? And then the mass of magnesium to get the mass of water, right? And so to get the total mass, I'm going to have to use my parts per million expression here, okay? So, and to use that, I got to find the mass of magnesium, right? So I'm going to first convert the moles of magnesium to mass. So 1 mole Mg2 plus times the molar mass, which we said was 24.3 grams per mole. And me 24.3 grams Mg2 plus, okay? I plug that in to my expression for my parts per million, 128 ppm equals 24.3 grams over the total mass. Okay, so m tot, what I'm saying for the total mass, times a million. Okay. So if I multiply the total mass on, right, so if I multiply both sides by the total mass, okay, right, I have 128 times m total equals 24.3 times a million. And then I will divide both sides by 128 to get that the total mass is 24.3 times 10 to the 6 divided by 128. Okay. That comes out to be just kind of round it there, 189,800 grams, okay, for your total mass, right? And so then I take my 189,800, set that equal to the mass of magnesium, which was 24.3 grams, plus the mass of water, right? Okay. And the mass of water is roughly equal to, again, when you do that subtraction and then round it, you're still going to round it up to just 189,800 grams, which if I convert that to kilograms, okay, divided by 1,000 grams for every 1 kilogram, okay, that's going to give me 189.8 kilograms, okay? And so then finally, my molality is equal to 1 mole, which is what we assumed, of Mg2 plus, divided by 189.8 kilograms of water. And that, I'll just do the calculation just to make sure, but that should come out to be, yeah, when rounded, 0.0053 mole hours, right? So again, it's the exact same answer as what we have up here. Okay. So, yeah, it's not, can't zoom out too much more than what I've already done, right? But the answers at the top and bottom of this page are the exact same, okay? So again, if I assume 1 mole of magnesium ions, I get the exact same answer, okay? Now, you know, for me, I feel like doing some of this math here to get the total mass is a little bit more complicated, you know, and so, so that's, again, why I typically look at, why I typically look at what's given here, and I assume some amount for what's in the denominator in the thing that's given, okay? So then all I have to do is take this number and multiply it by my assumption to get what's ever in the numerator, right? So I assume a total mass of 1,000 grams, take 1,000 grams, times it by 128 parts per million, divide by the 10 to the 6th, and I will get the mass of magnesium, right? But again, whatever assumption you make will work. You just got to make sure to be careful in how you're doing everything and converting everything, right? And you will get the same answer no matter what. So questions about this example? Other types of examples people want to see? Yeah, okay. Question here about colligative properties, right? Right, I mean, so I think the practice exam online might have, like, I forget, but there might be a question dealing with osmotic pressure, and I didn't talk about it this year, so we won't be doing that, right? So for colligative properties, right, there's 3 that we've talked about, boiling point elevation, freezing point depression, and vapor pressure lowering. The vapor pressure, we don't really have an equation that we've used to calculate how much the vapor pressure is lowered, okay? That's related with Raoult's law. I think Riley, the SI, maybe talked about it a little bit in the SI session, but we won't really use it here on the quizzes or exams, okay? So really the 2 we're concerned about is the freezing point and boiling point changes, right? And so we'll actually do a different one. Let's say I have, okay, yeah, let's say 125 grams of an unknown compound in 0.5 kilograms of water. The boiling point of this solution is 104.3 degrees Celsius, with the KB equaling 0.5, KB equals 0.54. What are units of the boiling point? Degrees Celsius per mole. Okay. And this unknown compound, I know it's a unknown molecular compound. That's key. Question is, what is the molar mass of my unknown molecular compound? Okay. All right. So that's the question. Okay. So this is a little bit more of a tricky colligative property question, right? The more straightforward questions are, this is the molality of my solution. What's the change in the boiling point, right? Like one of the quizzes questions was like that, okay? Right? And so here I wanted to do one that's a little bit more involved, right? Still a colligative property question, but there's like kind of an extra step to it, right?
Before you start,
Uh-huh.
why is it important that it's
So let's write out one of the equations we know, right? We know that the change in boiling point is with I, K, B, M, right? I here is your Van Hoff factor, right? It's how many things does that compound break apart into solution? Well, if it's an ionic compound, I don't like it could break off into 2 or 3 or 4 or 5 things in solution. I don't know, and it would make it impossible to solve the problem. So it being a molecular compound, that's telling you it's a non-electrolyte. That's telling you I is equal to 1. Okay, so we know I equals 1 because it's a molecular compound. Okay, right? That a molecular compound, right, is a non-electrolyte, organic molecules and things like that, right? And those guys just have a Van Hoff factor equal to 1, right? And so what we know is we know this relationship, right? We can delta TB we know is 4.3 degrees Celsius, okay? Right, because the regular boiling point of water is 100 degrees Celsius, so the change is 4.3, right? KB we're given, right? Now what we want to find out, right, is we want to find the molar mass of our compound, right? Right, well, the molar mass of something is defined, right, as the mass of that compound in grams divided by the moles of that compound, right? Well, we're given the mass of the compound, right? But we don't know the number of moles that are in that mass to figure out the molar mass. And so that is where this comes in, right? Because M here, molality, right, is defined as the moles of solute over kilograms solution, right? And we notice, right? And so again, this is knowing the definitions of these things is very helpful for solving these type of problems, right? Knowing that the molality is mole solute kilogram solvent, and my molar mass is my grams per mole, I can say, oh, hey, if I know the molality, I can find out what the moles are of my solute, and then I can calculate my molar mass, right? Given the mass of the solute, okay, and then the moles that I can get from the molality, right? And so what I'm going to be doing is I'm going to use this equation to get my molality, and then from my molality and the mass of my solvent, I can get the moles of my solute, and then plug that in to get the molar mass. Okay? So that's right the path that we want to take here. And again, if you haven't done many of these examples, right, and you're not familiar with, oh, that's what we need to do. Again, like I try to think about, okay, what things do we know? What equations do we know? And then, right, what are the things we're trying to get? Well, we're trying to get the molar mass. I don't know what the moles are of my compound in those grams, but I can find out how many moles in solution based off the molality, because the molality gives me the moles in solution per kilogram solvent, and I'm given the mass of the solvent, right? I'm given the mass of water, right, or solvent is 0.5 kilograms, right? So I'm given that, so I can use the molality to find that, okay? And so let's just kind of plug in things here. So 4.3 equals Van Hoff factor of 1, KB is 0.54, and then M here is our molality that we're trying to solve for. So we just divide both sides by 0.54, right? Get the molality equal 4.3 divided by, there we go, got it, 7.96 moles. Okay? Right? So that's the not mole, sorry, molal. Right? That's the molality, right? And again, molality is to find the mole solute kilogram solution, right? So I have 7.96 molal equals my moles of my moles solute divided by my kilograms of solvent. Sorry, that shouldn't say solution, let's just say solvent. Sorry about that. Kilograms solvent, which we know is 0.5, so it's 0.5 kilograms. So I just need to multiply 0.5 over to the other side. And that gives me my moles of my solute is equal to 3.98. And so finally, to get the molar mass, right? Let's get that molar mass. It's going to be the 125 grams, right? That was given in the problem. I'm told I have 125 grams in the solution, right? And then I divide it by my 3.98 moles, right? That gives me a molar mass of 31.4 grams per mole. Okay? So that is the molar mass of this unknown molecular compound. Okay? Great. And this type of approach is a very common thing to find, say, the molar mass of some unknown compound by just measuring colligative property change. Okay? You can measure temperature changes very precisely in your boiling points and things like that, or your freezing points. You can weigh out a substance very precisely to get the mass, and then given those two things, you can then accurately calculate what the molar mass is of some unknown compound in this approach. Now, there's maybe some other newer advanced techniques to do that, but this is something that has been used in labs, before to find molar masses of unknown compounds. Okay, by measuring some colligative property change, because again, a colligative property does not depend on the identity of the compound, just how much you have. Okay.
So this is molecular compound, the Van Hoff factor is always one, but it says ionic with NaCl, the Van Hoff factor.
Yeah, it'd be 2. But if it's an unknown ionic compound, I don't know, right? Because the ionic compound could be NaCl, it could be MgCl2, right? Or some other thing like that, right? K3PO4, right? And there, the Van Hoff factors are different for each one of these ionic compounds. So yes, for an ionic compound, you actually need to know what the ions are to figure out what the Van Hoff factor is. But a molecular compound, the Van Hoff factor is always equal to 1 because it's a non-electrolyte. It doesn't break apart in solution at all. All right, other examples or just questions about concepts or anything with the exam. And we will cover on Monday stuff related with reaction mechanisms, collision theory, and catalysts. Again, a lot of those, actually, none of those have some sort of numerical type questions that need to be answered. All of those are more kind of conceptual type stuff, and not so much kind of these numerical examples that we've been doing with conversions.
Do you know technically a problem where it like you find the average?
Okay. From what, like,
My notes, we had this one question, and like I think you went on like a little side tangent and like wrote it over here, and I just wrote 1
Oh, okay, yeah. Okay. So yeah, so for that, I know the problem you're talking about. So basically, problem that's being asked here is, you know, given a data here where I have like a concentration of A um, versus time, right? And let's say it starts off at 1.0, and then it goes down to 0.85, and then 0.65 and 0.45 or something like that, right? And my times here is 0, and then this is after 20 seconds, and then 35 seconds, and 110 seconds or something like that, right? Question is like, what is the average rate of reaction? Now, how I've written this data, probably the average over all of the data is, I have no idea. Like, I mean, we'll see what that kind of comes out to be, but really, what I think, right? So that I think the top of the slide says like the average rate of the reaction, and I think though in the question it should hopefully say something like, what is the average rate between each like time steps or something like that. So basically, the question is saying like, what is the average rate of the reaction between each measurement or time step, right? Measurement, right? So what is the average rate between here, the average rate between here, average rate between here? So we'll get 3 different average rates of reactions for these 3 different time intervals, right? Time step or interval, right? Right, and so for that, right, it's just that right, the average rate of the reaction, right? So let's assume this reaction is just like A going to B, or whatever, right? This is my reaction, right? The average rate of the reaction is going to be equal to the change in concentration of A over the change in time, right? So then from, time interval 1 to 2, right, that rate is just equal to change of concentrations. The final concentration is 0.85 minus the initial concentration of 1.0 over the time, 20 seconds minus 0, right? So that's 0.15 divided by 20, negative 0.15 divided by 20. That's minus 0.0075. And that has units of molarities per second. Okay. Rate always has units of molarities per second. Okay. From 2 to 3, right? My rate is equal to then 0.65 minus 0.85 over 35 minus 20. Okay. Which this is then what? 0.2 divided by 15. This equals, oh, there should be a minus sign here, sorry. Negative 0.2 divided by 15. So that gives me negative 0.013 moles per second. And then from 3 to 4, my rate is equal to 0.45 minus 0.65 over 110 minus 35, which equals negative 0.2 over 75. Gives me negative 0.0027 moles per second, right? Oh, sorry about that. Thank you. Yeah, sorry. Sometimes I forget where the thing is. So thank you. Yeah, right. And so that's what that slide was referring to. Now at the end, Yeah, at the very end, I calculated the average of all those numbers, which you could do, but you know, so I could do the average of these three numbers, right? Add the three up and divide by three, get the average over the entire time. But that's not typically as important as what is the kind of average rate over those time intervals from 1 to 2, 2 to 3, 3 to 4, right? Um, and so, yeah, that's how you would kind of do that, right? And so for this type of problem, you just be given a chart like this, right, and asked. And I think there might be an example of this on the sample exams or something like that, and asked to calculate the average rate. I think on the sample exam, it asks for the average rate over like all time or something like that. So for there, the like average rate over all time or something like that, right? That would just be, minus 0.0075 plus negative 0.013 plus negative 0.0027, all divided by 3, right? Literally the average of those three numbers. Which gives negative 0.0077, right? What that, so I think that's, if that's on the practice exam, I forget. I think it might be, that is what it's referring to, but so I think the answer on the practice exam is this, that you do this for each individual, like, step 1 to 2, 2 to 3, 3 to 4, and then you just take the average of those numbers to get the final numbers. And kind of clear that up.
Yeah, no, that definitely helps a lot. And like, I don't know. This is like one of the things that I like totally overcomplicate. And like now that I know, like there's just use information given and plug it in. I understand.
I mean, one of the things about this class is there's a lot of information given in, the course this semester, and it's a lot of different types of information, types of problems, types of things, right? We start talking about, I mean, they're all related sort of in the end, but like we start talking about intermolecular forces, which leads to solutions, which then we start talking about kinetics. We're going to start talking about equilibrium. Then we're going to start talking about acids and bases, and then we talk about the solubility of things, and then like we're talking about nuclear chemistry. So there's a lot of different concepts and different ideas that some are somewhat related to each other, but also sometimes very different. So the first time you see these things, can kind of be difficult to kind of say, oh, okay, this is related with what we were talking about here, or there, or somewhere else. So.
Yeah, and like the Chem one, I did not get like a good foundation of all, especially because I had it last semester and like switching like to online and everything. I thought it just wasn't a good time in Chem one. So now like going to Chem two, it's like I almost feel like I'm behind in some stuff, and so like I'm trying to like catch up while still like
Yeah.
trying to stay up. If that makes sense.
Yeah, I mean, so Chem 2 does use some things from Chem 1, but I mean, things are split up in the way they are between Chem 1 and Chem 2 to hopefully be relatively independent of each other in some ways. Now, there's a reason why you have to take Chem 1 before Chem 2, because there are some things in Chem 1 that you just have to know before Chem 2, but yeah. Any other last examples or questions people have before we finish up here? Just wait a second in case someone's typing something, or if you want, you can just speak. If that's the case, then we'll end kind of this review here. Like I said, I'll post this video online. And yeah, feel free, if you have further questions, feel free to email me, try to set up time for office hours, chat with me or other such things, okay?
Or